Somewhere in the constellation Aquarius, far beyond the reach of any unaided eye, a small coal red light burns in the dark. It does not flash or pulse. It does not sweep its light across the sky in the manner of something large and restless. It simply holds its position against the deeper black behind it, steady and extraordinarily dim, radiating heat in wavelengths the human eye was never built to detect. It is not a familiar kind of star. Held beside our own sun, it would appear less like a companion and more like an ember forgotten at the edge of a fire, a reddish-orange bead of warmth, patient, unhurried, and dwarfed so completely by the blazing lantern beside it that the comparison barely holds. This is TRAPPIST-1, and it has been burning there in that same quiet reddish way for longer than the Earth has existed. The first fact worth sitting with is its size. Our sun is a star of middling mass and middling volume, and it already exceeds anything our bodies can hold comfortably in mind. A sphere more than 100 times wider than the Earth, containing more than 300,000 times our planet's mass. TRAPPIST-1 is not that kind of star. Its radius measures about 12 hundredths of the sun's, so small that if the two were placed side by side in open space, the red dwarf would appear almost nestled against its companion, a coal-dark bead against a roaring furnace. To find something in our solar system that approaches its size, the nearest comparison is not a planet made of rock, it is Jupiter, the largest planet in our solar system, banded and immense by any human measure, large enough to contain more than 1,000 Earths by volume, nearly matches TRAPPIST-1 in diameter. The star is only marginally wider. Its body would wrap around the gas giant's equator, with just a thin margin of starfire to spare, a shell of nuclear fusion barely distinguishable in width from the world turning inside it. This is not a figure drawn to produce astonishment. It is simply what the measurements show, stated plainly and allowed to rest at its true scale. The mass follows from the size as it always does. TRAPPIST-1 contains less than 1/10 of the sun's mass, a fraction so small that it sits near the lower boundary of what can sustain hydrogen fusion at all. Below a certain mass, the pressures at the center of a collapsing gas cloud never reach the threshold needed to ignite the nuclear fire that defines a star. TRAPPIST-1 clears that boundary, barely, but with certainty, and the result is a star that burns by the same fundamental process as our own sun, but at such a low rate, and with such careful, almost miserly economy, that its fuel supply will last for timescales that belong to a different order of patience than any other number in ordinary astronomy. That extraordinary patience is inseparable from its smallness. It is one of the defining truths of this star. Because it burns so slowly, TRAPPIST-1 runs cool. The surface of our sun radiates at roughly 5,800 Kelvin, a temperature that produces the pale yellow-white light familiar from a clear afternoon sky. TRAPPIST-1 reaches only about 2,566 Kelvin at its surface, less than half the sun's temperature, and this cooler fire shifts the character of its light entirely. Where the sun peaks in visible wavelengths, TRAPPIST-1 radiates most of its energy in near-infrared light, wavelengths slightly longer than red, invisible to the human eye, and detectable only by instruments designed to see heat rather than color. The light it does produce in visible bands leans deep into the red end of the spectrum. That reddish-orange hue is not metaphor, it is the direct result of temperature. A heated body glows in a color determined by how hot it is, and at 2,500 Kelvin, the color is a deep, wine-dark red, the warmest and longest visible wavelength, the last color the eye holds as a flame cools to its limit. Stand in the path of that light if such a thing were possible, and the experience would be unlike standing in sunlight. The brightness overhead would be deeply reddened, the shadows tinged with color, the midday sky above a world in this system. Not the blue dome of Earth, but something darker, something almost amber. The warmth would be real, the infrared flux would be substantial. But the colors familiar on Earth, the green of leaves, the blue of water, the clear white of clouds, would all appear shifted and muted in this altered light, the entire palette of the world transformed by the simple fact of orbiting a cooler, redder, smaller star. What kinds of leaves a planet beneath this star might grow? What color the photosynthetic life would be if it existed? What shade the sand would take in the reddish late afternoon? These are questions that have no certain answers yet. But the quality of the light that would shape all of it is known, and it is this: dim, warm, deeply red, and falling from a source that never brightens into white. The star's surface temperature of 2566 Kelvin places it in the category astronomers call M-type, the most common classification for stars in the galaxy. Most stars are red dwarfs. The universe favors them overwhelmingly over the brighter, hotter, more massive stars that dominate the naked eye sky. Our sun, bright and yellow-white and comfortable overhead, is actually a minority type. Red dwarfs like TRAPPIST-1 make up something close to 3/4 of all stars in the Milky Way, burning quietly in their billions, most of them too faint to see without a telescope, holding the majority of the galaxy's stellar mass in dim, patient embers scattered through the dark. TRAPPIST-1 sits at the cool end, even within this category, classified more specifically as an ultra-cool dwarf, an M8 type, a designation that places it close to the very boundary of the stellar domain. It is a star, and a stable one, but it is the smallest and coolest kind of star that nature currently produces. Below it, a bit cooler and a bit smaller, are the brown dwarfs, objects that failed to ignite, that collapse and warm but never quite reach fusion, and below those, the gas giant planets. TRAPPIST-1 stands just above that threshold, nuclear fire burning at its center, holding its place in the stellar census by the narrowest of margins. A star's age is a different kind of number than its size or temperature. Size and temperature can be measured with some directness from its light. Age must be inferred from the star's chemical composition, from its position in the galaxy, from the known rates at which stellar populations age and evolve. The estimates for TRAPPIST-1 place its age somewhere between 7.5 and nearly 10 billion years old. The Sun, by comparison, is roughly 4.5 billion years old. The Earth formed not long after. The oldest rocks on this planet carry ages of about 4 billion years. TRAPPIST-1, on the most likely estimates, has been burning for roughly twice as long as the Earth has existed. Its planets, whatever their histories, have had time, a great deal of it, in which to develop, to be shaped by their star, to lose or hold their atmospheres, to settle into whatever equilibrium they now occupy. 7 billion years is not a number the body holds easily, but the weight of it matters here, because it means that whatever is true of those planets today, it has been becoming true for a very long time. And yet this age, extraordinary by the standards of Earth's history, is not even the beginning of TRAPPIST-1's potential lifetime. This is where the star's patient economy becomes genuinely staggering. Our sun, burning at its present rate, will exhaust the hydrogen at its core in roughly 5 billion more years. When that happens, it will swell, change, and ultimately die, as all stars die, each in its own way depending on its mass. TRAPPIST-1 will not do this anytime soon, because it burns so slowly, so carefully, sipping its hydrogen at a rate that our sun would consider glacial. And because its small, fully convective interior continually stirs and recirculates its fuel rather than depleting a central reserve, this star is expected to remain on the main sequence, steadily fusing hydrogen for somewhere between 4 trillion and 12 trillion years. Not billions, trillions, numbers that require a different kind of geography to understand, a different set of reference points. The universe itself is approximately 13.8 billion years old. TRAPPIST-1 is expected to live for at least 4 trillion years, nearly 300 times the current age of the universe. To step further along that comparison, when TRAPPIST-1 finally begins to die, the universe will be so old that the large spiral galaxies, like our own Milky Way, will have long since aged beyond anything recognizable. The smaller, longer-lived red dwarfs will be among the only active stellar lights left in a cosmos that has otherwise dimmed. The cosmic background, the faint warmth of the Big Bang, still detectable in all directions today, will have cooled to a temperature almost indistinguishable from absolute zero. The large stars that trace the spiral arms of galaxies now will be long dead. The medium stars will be white dwarfs, slowly cooling, and somewhere in the deep future, TRAPPIST-1 and stars like it will still be fusing hydrogen, quietly, coolly, redly, in a much darker and much quieter universe. This does not produce unease. Resting with that knowledge, it produces something closer to the feeling of leaning against something enormous and stable. The star does not burn with the extravagance of our sun. It does not race through its fuel or flare toward brightness in any self-destructive way. It simply continues, patiently, at the same reddish temperature, for timescales so large that they effectively mean forever on any scale a human life can touch. Whatever the planets circling it are doing right now, whatever chemical processes run on their surfaces or in their atmospheres, whatever equilibrium their climates have settled into, they have been doing it for billions of years already, and they will be doing it, in all likelihood, for trillions more. The star beneath which they orbit will not go away. It will not surprise them with an early death. It is the most constant kind of companion a planet can have. The light from TRAPPIST-1 takes time to reach us. All light takes time. That is one of the true plain facts of the universe, easy to state and quietly difficult to hold in full. Light travels at 299,792 kilometers per second, the fastest anything can move through empty space. Even at this speed, the distance between stars makes time unavoidable. TRAPPIST-1 lies approximately 40.5 light-years from Earth. This means the light arriving here tonight, the infrared glow from its surface, the dim reddish photons scattered outward in all directions, left that star more than 40 years ago. The light falling on any instrument sensitive enough to detect it is not the star's present self. It is a photograph, a message sent 40 years past and only now received. Any person standing on Earth tonight who was alive 40 years ago was alive when this light began its journey. Some who were young then are older now. Some who were children have grown and had children of their own. And all the while, that particular batch of reddish-orange light was crossing the dark between star systems at the fastest speed nature allows, reaching us now, after all of that, still traveling, still in motion, and only just arriving. 40 light-years is not a vast distance by galactic standards. The Milky Way is roughly 100,000 light-years across. Our nearest stellar neighbor, Proxima Centauri, is about 4 light-years away, but it is still an immensity by any human measure, a gulf so wide that no vehicle ever built by human hands could cross it in any time scale, a civilization would find comfortable. The fastest spacecraft ever launched by human hands travels at a small fraction of a percent of the speed of light. To reach TRAPPIST-1 at that speed would require tens of thousands of years. This is not a destination reachable by any current technology. It exists for now entirely as a target of light, something to be known only from a distance, studied only through the photons it sends toward us, understood only by the patient work of measuring how those photons arrive and what information they carry. Because TRAPPIST-1 is so dim, so much of its energy carried in infrared rather than visible light, it appears in the sky at an apparent magnitude of roughly 18.8. Magnitude is the astronomer's scale for brightness as seen from Earth, and the scale runs in a direction that surprises people new to it. Brighter objects have lower numbers, dimmer ones have higher. The human eye, under a clear dark sky away from city light, can see stars down to about magnitude 6. TRAPPIST-1's magnitude is nearly 19, 13 steps fainter than the limit of unaided human vision. To put a felt comparison on it, the dimmest star visible on a clear country night is already 1,000,000 times brighter than TRAPPIST-1 appears from Earth. It does not appear in any historical star catalog. It was not known to any ancient astronomer. No traveler in any century before powerful telescopes existed was aware of it. It exists from the perspective of human perception only within the era of sensitive electronic detectors, discovered and named and studied within the lifetime of many people now alive. It lives in the constellation Aquarius, which spreads across the southern celestial hemisphere, a large, irregular grouping of stars that represents a water bearer in the ancient sky maps, pouring a stream of water toward the constellation Pisces, Austrinus to the south. On a clear winter night, Aquarius rises in the southwest and sets before midnight in the northern hemisphere, its brightest stars visible but unremarkable, modest white and yellow points that the eye passes over without lingering. Somewhere within that grouping, at coordinates no casual observer would ever find without assistance, TRAPPIST-1 sits in the dark. It is invisible, completely, totally invisible to any unassisted human eye, and yet it holds 7 planets. 7 worlds orbiting that invisible point, some of them the right size and the right distance from their star, to make scientists look very carefully at the question of what conditions they carry on their surfaces. A system of some complexity and some importance to the question of whether Earth-like conditions exist beyond our solar system, and it is invisible. It requires a telescope of real power even to detect its presence, let alone to study it. The telescopes that found it and that continue to study it are not romantic instruments in the older sense, not the polished brass of a 19th century dome, not the hand-guided mirrors of a Victorian observatory. They are robotic. They operate automatically under the guidance of software, pointing themselves at targets chosen by astronomers working at computers far away. They are built to be patient in a way that human observers never quite managed, watching the same star for hours, for nights, for weeks, recording its brightness in data streams that are then analyzed long after the night has passed. Patience, in this kind of astronomy, is not a virtue exercised by people under a cold sky. It is built into the hardware. The telescope sits on its hilltop, collects photons, and waits, all without anyone watching, all through the dark hours of many separate nights, quietly accumulating the evidence from which worlds are eventually inferred. The evidence begins with brightness. A star shines with a certain measured output, stable from night to night within the limits of its own variability. When something passes in front of it, something between the star and the telescope, a small fraction of that light is blocked. The star dims, briefly and by a tiny amount, and then returns to its previous brightness when the obstruction has passed. This is the signature. It is not a dramatic event. The dip in brightness for a planet crossing TRAPPIST-1 amounts to a small fraction of the star's total output, a few percent for the larger worlds, a fraction of a percent for the smaller ones. Against a star the size of our Sun, Earth-sized worlds would produce a dip so small it would be extraordinarily difficult to detect. But TRAPPIST-1 is small, because the star itself is only marginally wider than Jupiter. An Earth-sized world crossing its face blocks a much larger proportion of its light, a dip large enough to detect with appropriate instruments, large enough to measure precisely, large enough to reveal the size of the world doing the blocking. This is the great gift that TRAPPIST-1's smallness offers to those studying it. A small star makes small planets visible in ways they would not be around larger stars. The signal from an Earth-sized world crossing a Sun-like star is difficult and uncertain. The signal from that same world crossing TRAPPIST-1 is a clear and measurable event. This is why this particular star, out of the billions of red dwarfs in the galaxy, became the focus of a careful, extended watch, and why that watch eventually resolved into the discovery of 7 worlds, where before there had seemed to be only a point of dim reddish light. The star did not change when those worlds were found. It was not newly illuminated by discovery, not shifted from its position, or altered in its slow burning. It remained what it had always been, a small coal-red ember in the dark of Aquarius, radiating heat in wavelengths the human eye cannot detect, orbited by 7 worlds it had been keeping for billions of years before anyone on this planet thought to look. The finding changed only the knower, not the known. There is something in the quality of TRAPPIST-1's light that rewards dwelling on. It is not cold. Ultra-cool is the astronomical term, meaning cool relative to other stars, cool relative to the blue-white giants burning at 40,000 Kelvin, cool relative even to our own sun. But 2,500 Kelvin is still an extraordinary heat by any earthly measure. It is the temperature of molten iron. It is the temperature of a cutting torch's flame. By the standards of matter as experienced in everyday life, it is incandescent, a genuine fire, producing genuine light, warming the surfaces of its planets in a genuine and measurable way. The term ultra-cool describes where it sits on the stellar temperature scale. It does not mean the star is cold. It is burning. It has been burning for 7 billion years or more, and it will go on burning at that same careful crimson rate long after the sun that lights our own sky has completed its life and settled into cooling ash. The coal-red glow that TRAPPIST-1 produces travels outward in all directions at the speed of light, spreading across space in an expanding sphere of energy. Most of it passes through empty space and reaches nothing. A tiny fraction of it strikes the 7 planets in their close orbits, warming their surfaces and atmospheres according to how far they sit from the source. A fraction of the rest escapes those planets and continues outward through the outer edges of the system, through the thin medium of interstellar gas and dust, across 40-plus light-years of open space, and arrives here at this solar system at the instruments trained on it, as a whisper of infrared radiation, encoding the temperature and composition of everything it passed through and reflected from. It is an extraordinarily faint signal from an extraordinarily dim source, and yet it carries, in principle, everything there is to know about that star and the worlds around it. If the instruments are sensitive enough, and the observers patient enough, and the physics well enough understood to read what the light contains. The patience required to understand this star mirrors the patience of the star itself. Nothing about TRAPPIST-1 is quick. Its light takes 40 years to cross the dark between it and Earth, Its planets take only days to complete their short orbits, but the accumulation of enough observations to measure those orbits precisely, to determine the sizes and masses of all 7 worlds, to begin to probe their atmospheric properties. This has taken years of dedicated telescope time, years of data analysis, years of careful scientific work, whose pace is closer to the pace of the star than to the pace of a news cycle. The star burns slowly. The science accumulates slowly. The knowledge deepens over time, rather than arriving all at once. Outside, somewhere above the city lights or below the horizon, depending on the season, Aquarius has either risen or set. Its brightest stars, the ones that history named and mythologized, the ones that any attentive eye can find on a clear night, are arranged in their familiar pattern, a gentle arc and scattered grouping that ancient sky watchers saw as a figure pouring water. And somewhere in that grouping, at a position that requires precise coordinates to identify and a powerful telescope to confirm, TRAPPIST-1 holds its place. It does not announce itself. It does not compete with the brighter stars around it. It simply occupies its coordinates, radiates its reddish light in every direction, holds 7 planets in their close synchronized orbits, and continues as it has continued for nearly 10 billion years, to burn. The feeling that attaches to this, resting with it in the dark, is not the excitement of novelty. It is something quieter. It is something closer to the feeling of learning that something ancient has been present all along, unnoticed, waiting in plain sight, or in this case, in invisible proximity to plain sight, just beyond the threshold of human perception, just one wavelength into the infrared, just one magnitude too faint. TRAPPIST-1 has been there for the entire history of human astronomy. Every stargazer who ever lay on their back and mapped the sky with their eyes was lying beneath a sky that contained this star, unknowing. Every generation that watched Aquarius rise and set in the autumn sky was watching a sky that contained this dim point, holding its worlds in perfect silence and perfect darkness, visible to no one. And the star did not mind. Stars do not mind. They simply burn, or do not burn, at the rate and temperature their mass dictates. TRAPPIST-1's rate is low. Its temperature is low. Its brightness, by any measure that touches the human eye, is almost nothing, but its longevity is extraordinary. While the great blue giants that light the most dramatic regions of the galaxy burn themselves out in millions of years, spending their fuel in a gorgeous and wasteful rush, TRAPPIST-1 barely draws on its reserve. 4 trillion years is the low estimate for its remaining lifetime. 12 trillion is not ruled out. The numbers are so large that any comparison to human experience fails before it begins, and the better response is not comparison, but simply rest. The star is there. It will be there. It will be there long after this conversation, long after this planet, long after the sun, long after anything that now exists in the universe, except the very smallest and most patient stars. The light it emits tonight is the same light it emitted last year, the same light it emitted a billion years ago, within the variations of its ordinary activity. The same reddish-orange infrared glow spreading outward at the speed of light, reaching across 40 light-years to arrive as the faintest possible whisper at the edge of detectability, a whisper that took 40 years to cross the dark, that left the star before some of the scientists who study it were born, that carries in its frequency and intensity the quiet record of everything the star is, its temperature, its size, its age, its patient burning, arriving here, now, in the instruments that were built specifically to receive it. The star is not dramatic. That is worth saying plainly. It does not flare with the violence of a large young star, does not heave in and out like a pulsating giant, does not stream material in great jets or puff into a nebula. It holds its radius, it holds its temperature, it holds its 7 worlds in their close orbits, and it burns steadily and redly and invisibly at the low end of the stellar spectrum, producing light that the human eye cannot see and heat that only the most sensitive instruments can measure across 40 light years of space. There is a particular kind of peace in that, the peace of something that does not seek attention, the peace of something that has found its rate and held it without variation for billions of years, and will hold it without variation for trillions more. In the dark of Aquarius, at coordinates too faint for any unaided eye to resolve, the ember holds. The reddish light spreads outward in its slow sphere. The 7 worlds circle in their short days, their surfaces warmed by a heat the human eye cannot see, their atmospheres, whatever they contain, brushed continually by infrared radiation from a star that will still be burning when the concept of a year has no remaining reference point against which to be measured. The star does not know it is being studied. It does not know its name, or the names of its planets, or the names of the people who watched it patiently for years until its worlds revealed themselves in a series of tiny periodic dimmings. It simply burns at 2566 Kelvin, at a radius barely wider than Jupiter, in the silence of the dark between stars, slowly, patiently, for a time so long it has no common name. Burning still, the star holds still. Its light does not vary by much. Most nights, most hours, it puts out the same faint reddish glow, steady, patient, almost imperceptible to any instrument not specifically trained on it. At the Lucia Observatory in Chile, on a dry hilltop above the Atacama, a small robotic telescope pointed toward the constellation Aquarius and watched, not once, not briefly, night after night, month after month. It recorded the brightness of a star, too faint for any human eye to find without help, a star so dim it had been catalogued and largely passed over. The telescope watched, and the star almost imperceptibly dimmed. That first dimming was not dramatic. It was a shallow notch in a brightness record, a drop of less than 1%, lasting a few hours, then a return to baseline. On a larger, brighter star, it would have meant almost nothing. But this star was small, extraordinarily small, small enough that even a world no wider than the Earth, crossing its face, could block a meaningful fraction of its light. And so the dimming was real. The dimming was a shadow. The shadow was a world. Transit photometry works by patience and precision. A telescope holds a star in its field of view and measures its brightness at regular intervals, building a record that stretches across days and weeks and months. For most of that record, the brightness is flat, constant, a horizontal line. Then something crosses the star, a planet, moving along its orbit, passing between the telescope and the stellar disk, and the brightness falls. Just slightly, just briefly, then it returns. The geometry is simple. The more of the star the planet covers, the deeper the dip. The longer the crossing takes, the wider the orbit. The time between one crossing and the next tells the length of the year. From these 3 numbers, depth, duration, period, the outlines of a world can be sketched. What the robotic telescope at Lucia was doing on those clear Chilean nights was listening for the silences in the light, the pauses, the almost nothings. And gradually, with accumulating care, a pattern emerged from the record that was not noise and not error, and not instrument drift. It was periodic. It was repeating. It was, in the quiet language of the method, a transit. The telescope was named TRAPPIST, the Transiting Planets and Planetesimals Small Telescope, a 0.6-meter instrument operated from the University of Liège in Belgium by a team led by an astronomer named Michael Guillon. It had been built to watch small, cool stars, stars like the one in Aquarius, because the mathematics of transit detection favor small stars enormously. Around the Sun, an Earth-sized world blocks 1 part in 10,000 of the light. Around TRAPPIST-1, which is barely larger than the planet Jupiter, that same world blocks nearly 1 part in 100. The signal is amplified simply by the smallness of the stage. In May of 2016, the team announced that TRAPPIST-1 had planets, 3 of them, 3 small worlds orbiting close in, their transits detected in the brightness record, with enough confidence that the announcement could be made and trusted. The number alone was notable, but what came next was something else entirely. Further observations, gathered from ground-based telescopes around the world, and eventually from the Spitzer Space Telescope, extended the record. The brightness curve of TRAPPIST-1 grew longer and more detailed, and in those added hours and nights of data, more dips appeared. Dips with different depths, dips with different periods, dips that, when separated from one another and analyzed individually, resolved into 4 additional worlds, 4 more planets crossing the same small star, each on its own quiet orbit. In February of 2017, the full count was announced. Not 3, 7. 7 planets had been found orbiting a single star. 7 distinct worlds, each leaving its own periodic shadow in the light of one small reddish point in Aquarius. No system of this kind, this many planets, this temperate, this close to their star, had ever been identified around any other sun. The robotic telescope on the Chilean hilltop, standing no taller than a person and looking like something assembled from ordinary parts, had become the instrument through which one of the most complex planetary systems ever found was first recognized. Its name, given to the telescope before any of this was known, passed to the star, and then to the system, and then into the vocabulary of everyone who works on exoplanets and anyone who has read about them since. TRAPPIST, a name from a small telescope on a dry hill, now attached to 7 worlds. The brightness curve grew into something extraordinary once all 7 planets had been confirmed. Held up as a graph, it looked like a record of steady light, interrupted at regular intervals by a series of overlapping rhythms, some dips deep and brief, some shallow and long, some arriving so frequently they seemed to pile on top of one another. Each dip had its own signature. Each signature had its own period, and the periods, when placed side by side and examined, revealed something that no simple accident of nature could produce. The 7 planets orbit TRAPPIST-1 in a resonant chain. Resonance, in orbital mechanics, is a relationship between periods, a situation where 2 or more planets complete their orbits in whole number or near whole number ratios to one another. 2 orbits here for every 3 there. 8 orbits of one world for every 5 of its neighbor. These ratios are not coincidental, they are gravitational. When 2 planets repeatedly encounter each other at the same points in their orbits, they exchange tiny gravitational nudges that accumulate over time and eventually settle into a stable rhythm, a locked relationship that self-maintains. Planets in resonance are like pendulums that have been coupled. They reinforce each other's timing, they resist disruption, and they persist in their arrangement for vast spans of time. What makes the TRAPPIST-1 system unusual is not that 2 or 3 of its planets share a resonant relationship. What makes it unusual is that all 7 are resonant with one another, forming a chain that runs continuously from the innermost world to the outermost. Each planet is locked in rhythm with the one inside it and the one outside it. The whole system pulses in a single coordinated sequence. Imagine it not as a picture, but as a sound. Each planet completing its orbit marks a beat. The innermost world beats fastest, once every day and a half. The next world takes 2.5 days, then 4, then 6, then 9, then 12. The outermost world, the farthest out, takes nearly 19 days. And within those rhythms are the resonances. The second planet completes 8 orbits for every 5 of the third. The third and fourth are locked in 3 to 2. The fourth and fifth in 4 to 3, and so on, all the way out. Not perfectly, close enough that the deviations from the ideal ratios are small and systematic, but not so close that the system is rigid. It breathes slightly. It oscillates around its resonances rather than snapping into them. But the pattern is there, and it runs through all 7 worlds at once. This kind of chain does not form in place. The orbits of the 7 TRAPPIST-1 planets are extraordinarily compact. All 7 worlds fit inside a circle smaller than the orbit of Mercury around the Sun. Mercury, the innermost planet of our own system, takes 88 days to complete its year. The outermost TRAPPIST-1 planet, TRAPPIST-1H, takes fewer than 19. The whole architecture is compressed into a space that, set beside our solar system, would seem almost impossibly tight. That compression, combined with the resonant chain, tells a story about how the system came to be. The 7 planets almost certainly did not form where they now orbit. Material close to a young star is sparse, stirred, and hot, not the quiet, dense environment where solid worlds tend to grow. The planets most likely formed farther out, where gas and ice and dust were more abundant, and then migrated inward through interactions with the disk of material that surrounded the young star in its early years. As they migrated, they encountered one another's gravity. The resonances formed gradually as the planets settled into relationships that allowed them to move together without destabilizing each other. By the time the disk dissipated and the migration stopped, the 7 worlds had arrived at something stable, a chain that has since persisted across billions of years. It is a slow, old system, patient and self-reinforcing, built over geological time, and maintained by the same gravitational rhythms that first assembled it. The 7 planets are designated by letters. The star itself is denoted with the letter A, not because anything crosses the star's face to signal it, but because the naming convention reserves the first letter for the host. The planets follow in the order they were confirmed, lettered from B through H, TRAPPIST-1, B, C, D, E, F, G, H. The letters track outward. TRAPPIST-1b is the innermost world, orbiting in just over a day and a half. TRAPPIST-1h is the outermost, completing its year in just under 19 Earth days. TRAPPIST-1b orbits at a distance of roughly 0.011 astronomical units from its star. 1 astronomical unit is the average distance from the Earth to the Sun, about 93 million miles. TRAPPIST-1b, the innermost of the 7, orbits at just over 1% of that distance. It is closer to its star than our own moon is to Earth. At that proximity, it receives more than 4 times the stellar energy that Earth receives from the Sun. Moving outward, the distances grow. Each successive planet orbits a little farther out, receives a little less energy, completes its year a little more slowly. By the time the chain reaches TRAPPIST-1h, the outermost world, the distance from the star has grown to roughly 0.063 astronomical units, still only 6% of the Earth-Sun distance, but far enough that the stellar energy reaching that world is only a small fraction of what bathes the innermost planet. The whole family fits inside a space that around our sun would hold nothing but empty room well inside the orbit of our closest neighbor. What matters, standing back from the distances and the designations, is the shape of what this implies. 7 worlds, one small star, all 7 in perpetual orbital resonance, their gravitational voices tuned to one another, their positions in the system as coordinated as the parts of a mechanism that has been running for billions of years without interruption. The image that returns when thinking about the discovery of this system is the brightness curve of the star, that long horizontal line of steady light, and then the dips. Each dip was made by something real, not a glitch, not a fluctuation in the detector, not a ghost in the data. Something with a surface and a mass and an orbit, something that had existed for billions of years before any telescope was pointed at the region of sky it crossed the face of its star, and left a mark in the light, a mark so small that it required a dedicated robotic instrument to find it, and weeks of accumulated data to trust. The first dip found, then a second, with a different period, then a third. Then, as more telescopes joined the effort and the data record grew, 4 more, 7 shadows, 7 transits, 7 worlds, each one announcing itself in the only way available to it from 40 light years away, by briefly, very slightly, dimming the star. The star's brightness record, stretched across weeks, held all 7 signals at once, overlapping and interleaved, their different periods and depths sitting side by side in the data like distinct voices in a sound. Separating them required patience. Modeling the orbit of each world while accounting for the influence of all the others required more. The resonant chain complicated the analysis and enriched it simultaneously. The gravitational interactions among the planets caused each transit to arrive slightly early or late, pulled forward or back by the combined weight of 6 neighbors, and those timing deviations, measured in minutes, sometimes seconds, carried information about the masses of the worlds. The same chain that made the system remarkable also made it possible to weigh its members from the timing of their shadows. This is a quieter kind of discovery than most. There is no image of the TRAPPIST-1 planets, no photograph, no surface glimpsed, no cloud pattern resolved, no feature identifiable from any picture taken. What exists is a record of light fluctuations, thousands of individual brightness measurements accumulated over months and years, from which the existence of 7 worlds has been inferred with enough precision that their sizes and orbital periods are known, their masses estimated, and their relative positions within the system mapped in detail. Every planet in the TRAPPIST-1 system is known through subtraction, through what it took away briefly from the light of its star. There is something restful in that, if one holds it long enough. The faintest kind of evidence, the smallest signal that can be trusted, and from it, 7 worlds. The resonant chain, when imagined as a physical thing in space rather than a pattern in numbers, takes on a particular quality. The 7 planets are not evenly spaced. They are close together, all of them circling a star barely larger than a gas giant, their orbital distances measured in fractions of what separates the Earth from the Sun. From the innermost world to the outermost, the chain spans roughly the same distance as from the Earth to the Moon, a span that by any cosmic measure is vanishingly small. 7 worlds inside the space the Moon traverses. In that compactness, The planets are never truly far from one another. TRAPPIST-1c and TRAPPIST-1c, the two innermost worlds, are separated by a gap that on certain alignments would allow a person on one to see the other as a bright disk against the sky, not a point, as planets appear in our own sky, but an object with perceptible size. The inner worlds, in particular, are close enough in their orbits that the gravitational fingerprints they leave on one another's timing are strong enough to measure precisely. The chain is not abstract. It is a set of real physical relationships among real worlds whose mutual gravity is measurable and has been measured. The resonant chain also implies stability. A system in deep resonance is not easily disrupted. The gravitational relationships that lock the planets into their coordinated rhythms also distribute and dissipate the energy of any disturbance, a passing object, a slight perturbation, an asymmetry in how the system formed. Over billions of years, these stabilizing resonances have held. The system that the telescope at La Silla first glimpsed is an old one, and the arrangement it holds has been its arrangement for most of its long history. What was found was not a system in formation or in flux, but a system arrived at its settled state. The La Silla hilltop, when imagined on the nights when the data was being gathered, holds a particular kind of stillness. The Atacama region is dry enough that the atmosphere above it is unusually transparent, low humidity, few clouds, the air thin and cold at altitude. The 6-meter telescope tracked its target automatically, adjusting for the rotation of the Earth, keeping the same faint point in Aquarius centered in its field while the sky slowly wheeled around the polar axis. No human eyes were involved in most of this. The telescope was robotic. It opened and closed, and tracked and recorded on its own, logging thousands of brightness measurements night after night, building the record from which 7 worlds would eventually emerge. The astronomers working with it were not watching in real time. They reviewed the data afterward, looking for patterns in the accumulated record, testing candidate signals against instrument noise, fitting orbital models to the timing data, and gradually, over months, arriving at conclusions that could be stated publicly. This is patient work. It is not dramatic in its execution. It is the slow accumulation of evidence, each piece unremarkable on its own, each piece necessary to the next. When the first 3 planets were announced in May of 2016, the team knew the data already hinted at more. The brightness record contained dips that the 3-planet model did not account for. Those unexplained dips were not nothing. They were too periodic, too consistent, too structured in their depths and durations to be noise. But confirming them required more data, more observation time, more nights of the telescope tracking that faint point in Aquarius and logging its light. The Spitzer Space Telescope, operating above the atmosphere in infrared wavelengths, well suited to the reddish emission of TRAPPIST-1, added weeks of continuous coverage that no ground-based observatory could provide. And from that extended record, the remaining 4 planets resolved themselves clearly enough that they could be named. February 2017 brought the full announcement. 7 planets, 1 star, the most planet-rich temperate system ever identified around any other sun. Papers were submitted and published and read. The name TRAPPIST-1, already in use among researchers who followed the field, spread outward into broader attention. And the system, that compact, resonant, ancient chain of 7 worlds orbiting a dim reddish star 40 light-years away, became the subject of sustained scientific inquiry that has continued without interruption since. The brightness curve of TRAPPIST-1 extended and refined across years of subsequent observation has grown into one of the most precisely characterized planetary records in the history of exoplanet science. The orbital periods of the 7 planets are known with exceptional accuracy. The sizes of the planets derived from the precise depths of their transits are known to fractions of an Earth radius. The masses derived from the gravitational timing variations are known to within a few percent for most of the 7. What began as a series of barely detectable dips in a faint star's light has become a detailed architectural map of an entire planetary system. The 7 worlds orbit. They have always orbited. Long before the telescope on the Chilean hilltop turned in their direction, long before any instrument built by human hands was capable of detecting them, they were crossing their star's face in the same steady sequence, leaving the same periodic shadows in the same proportion of light, following the same resonant chain they have followed since they settled into it, billions of years ago. The discovery changed nothing about the system. It changed only what was known. There is a particular kind of scale at work in the TRAPPIST-1 system that resists simple description. The 7 planets are not small in any absolute sense. They range from roughly a third of Earth's mass to somewhat larger than Earth. But in the context of a system whose entire architecture fits inside the moon's orbit around the Earth, their distances from one another and from their star feel intimate, compact, almost enclosed. 7 worlds within a space that by any cosmic measure is nothing. And yet each world is a world, a body with a surface, and an interior and an orbit and a mass capable of holding an atmosphere, capable of receiving starlight, capable of existing as a place. The resonant chain holds this intimacy in place. Without the stabilizing gravitational relationships among the 7 planets, orbits this close together would be chaotic. The planets would perturb each other into crossing paths, destabilizing the system over timescales of millions of years rather than billions. The resonances prevent this. They are not a coincidence the system happens to be in. They are the condition that allows it to exist as it does, long enough for any of it to matter. The star in the middle of all this, the small reddish ancient point in Aquarius, continues to do what it has done for 7 or 8 or 9 billion years. It burns, slowly, quietly, with a surface temperature so low that most of its light comes out in wavelengths below what the eye can process, in the near infrared rather than the visible. Its output is steady by the standards of stellar timescales, though not without its flares and eruptions. It holds its 7 worlds in their resonant chain with the patient indifference of gravity. And from a hilltop in the Atacama, or from a telescope in orbit above the Earth's atmosphere, its brightness dips and recovers and dips again, each dip a world, each world a dip, the whole record a slow, repeating score of 7 instruments playing together around a single quiet flame. The 7 planets do not know they are in resonance with one another. Gravity is not a language. Nothing in the TRAPPIST-1 system chose its orbital period or tuned its rhythm to fit the one inside it. What exists is the result of physics operating over billions of years. Migration, interaction, dissipation, and settling, all of it governed by equations that do not require a mind to run. The resonances emerged, the chain formed, the system found its stable configuration, the same way water finds the lowest available level, not by seeking it, but by arriving there through the accumulated action of forces that were always present, and there the chain remains. 7 worlds spaced along the same narrow ring of orbital space, each one completing its year in a period mathematically related to those of its neighbors, all of them circling a star so small and cool and old that it will still be burning when the Milky Way has changed beyond any recognition it carries today. The robotic telescope that found them has continued its work. The star has continued its slow, patient burning. The planets have continued their synchronized orbits. And the brightness curve, that flat line interrupted by 7 distinct periodic dips, continues to accumulate data points, one measurement at a time, in the cold, dry air above the Atacama. The first dimming was a shadow. The shadow was a world, and the world, it turned out, was one of 7, all of them arranged in the most orderly orbital chain ever found around any other star. 7 moving pieces turning in patient, mathematical harmony around a dim coal red light 40 light years away in the dark. The habitable zone is not a place. It is a band of warmth, a narrow ring of orbital space around a star, where the energy arriving at a rocky surface falls within a range that liquid water can tolerate. Too close, and the heat drives every drop of water skyward. Too far, and the cold locks it beneath ice, too thick to melt. The ring is defined entirely by the star it encircles, and around TRAPPIST-1, a star so dim and cool that its energy output is only a fraction of our sun's, that ring sits extraordinarily close in, a narrow corridor of warmth drawn tight against the star's reddish glow. 3 of the 7 worlds that orbit this small star fall within that corridor, or close enough to its edges that the difference matters only to the thickness of whatever atmosphere each world happens to hold. Those 3 worlds, the 5th, 6th, and 7th from the star, in terms of their position in the known family, have names made of a letter and a number, and they carry within their bulk and their orbits a question that no measurement yet made has fully resolved. The innermost planet sits beyond the habitable zone's inner boundary, almost certainly too warm for standing water in most scenarios that scientists can model with current knowledge. The outermost known world orbits well beyond its outer edge, a cold and quiet place that almost all models place beneath permanent ice. Between these 2 extremes, the 3 temperate worlds move in their slow, resonant paths, each receiving a share of the star's infrared light that falls somewhere in the range life as it is known on Earth would recognize, not comfortably, perhaps, but within the physical boundaries of the possible. Before any of those 3 worlds can be understood individually, the gradient must be felt, from the innermost to the outermost. The energy arriving at each successive orbit diminishes. It does not fade abruptly. It steps down the way heat leaves a fire as a body moves slowly away from it, not cut off, but thinning, each distance receiving less than the one before. The innermost of the 7 planets receives roughly 4¼ times the energy Earth draws from its own sun. That is a fierce and unrelenting heat. Moving outward through the system, each world receives less. The 2nd planet receives about 2½ times Earth's insolation. The 3rd, a little more than Earth's own share. The 4th, still more moderate, close to the inner edge of the habitable ring. And then the 3 temperate worlds begin. The 5th, 6th, and 7th, receiving 66% of Earth's flux, then 38, then 26. Each step outward is a step deeper into a cooler, quieter sort of light. The 8th world, the outermost known, receives just 14% of what Earth receives from the sun. At that distance, even generous atmospheric models leave its surface cold. It orbits at the edge of warmth, in a place where the star's light arrives thinned and reddened, and not quite enough on its own to keep the surface from freezing solid. The concept that matters most in understanding each of these worlds individually is one called equilibrium temperature. It is the temperature a rocky body would settle into if it had no atmosphere at all, a bare sphere of rock or ice, absorbing its portion of the star's energy and radiating it back into space with nothing to trap any warmth. Equilibrium temperature is not a prediction of what a planet's surface actually feels like. It is a starting point, a baseline, the raw thermal floor from which all atmospheric effects, all greenhouse warming, all reflective properties must be calculated upward or downward. It is what the planet would be without any help or hindrance from chemistry. For the fifth planet from the star, the first of the three temperate worlds, that equilibrium temperature works out to roughly 251 Kelvin. That is cold. On the Celsius scale, it falls about 22 degrees below the freezing point of water. Unmodified by any atmosphere, the surface of this world would be a frozen place. But the same is true of Earth. Strip Earth of its atmosphere, its carbon dioxide, its water vapor, the thin chemical blanket that holds warmth against the surface, and the equilibrium temperature of this planet drops well below freezing. It is the greenhouse effect, the trapping of outgoing heat by atmospheric gases, that pushes Earth's average surface temperature from a frozen baseline up into the range where liquid water flows across the surface in rivers and gathers in deep oceans. On the fifth planet of the TRAPPIST-1 system, a greenhouse warming of roughly 20 to 30 Kelvin from a moderate atmospheric composition would be physically sufficient to push the surface temperature above the freezing point. That is not a large requirement. Carbon dioxide, water vapor, and nitrogen in proportions broadly similar to those found on Earth or Mars, in different ratios and concentrations, could provide it. Climate models suggest that liquid water on this world's surface is not merely possible, but genuinely plausible under a reasonable range of atmospheric scenarios. The fifth planet of TRAPPIST-1 is known by the designation TRAPPIST-1e. Its radius is estimated at close to 9/10 that of Earth. Its mass is estimated near 7/10 of Earth's. These numbers, taken together, suggest a world broadly rocky in composition, built from silicate material, with a surface gravity slightly less than Earth's, enough less to be measurable, but close enough that the difference would be felt only faintly. Of all the worlds yet found beyond this solar system, it sits among the nearest physical analogs to Earth in bulk properties, surface gravity, and received energy, all three at once. Most exoplanets that receive roughly Earth's share of energy from their stars are much larger, or orbit stars whose radiation environment differs sharply from what Earth experiences. TRAPPIST-1e, small and rocky, and receiving about 2/3 of what Earth receives, comes closer than most to the set of conditions that produced, on one world, an ocean-covered surface where chemistry could complexify over billions of years. 2/3 of Earth's insolation is not nothing. 2/3 of the sun's warmth at Earth, arriving from a star whose light is redder and deeper in the infrared, would bathe a surface in something that might be imagined as the quiet, diffuse light of a heavily overcast autumn afternoon, warm enough, even enough, with nothing fierce or glaring about it. The star in the sky of this world would appear large, larger in angular terms than the sun appears from Earth, because the orbit is so close. Even dim, even small, a star 400 times closer than the sun would hang visibly large in whatever sky its planets possess. The light would carry a warmth of the sort that does not burn. It would come from an object that appears to the eye, if any eye were present, as a deep, dull reddish-orange disk like an ember from a fire viewed in full dark, before the fire has quite gone cold. Whether any eye, any chemistry, any process that deserved the word life, has ever experienced that light is a question no observation yet made can answer. What is known is that the physical parameters do not rule it out. Among the habitable zone planets, TRAPPIST-1e is the one that demands the least from its atmosphere to maintain surface liquid water, requires the fewest extraordinary conditions, and presents the closest match to the kind of environment where life, in its most familiar form, is known to operate. That is not evidence of life. It is simply the quietest physical argument for the possibility. The sixth planet in the system, TRAPPIST-1f, moves in an orbit slightly farther from the star. Its year, the time it takes to complete one full circuit, is just over 9 Earth days. At that distance, it receives approximately 38% of the energy Earth draws from the Sun. The equilibrium temperature for a bare, atmosphere-free version of this world comes out near 219 Kelvin, roughly 54 degrees below the freezing point of water. That gap is larger than the one facing the fifth planet. It requires more from an atmosphere to close. Greenhouse warming of 50 to 60 Kelvin from a richer or denser atmospheric composition would carry the surface temperature above freezing. That is not beyond the range of physically plausible chemistry, but it requires more specific conditions than the world inward of it does. What makes TRAPPIST-1f worth close attention is not just its position in the system, but what its bulk properties suggest about its interior. When a planet's size is known from the fraction of a star's brightness it blocks during a transit, and its mass is known from the gravitational signature it leaves in the precise timing of neighboring worlds' transits, the two numbers together yield a density, and density, in a rough and preliminary way, speaks to composition. For TRAPPIST-1f, the density that emerges from these measurements falls below what would be expected for a purely rocky world. It is lower than Earth's density, lower than what the inner silicate planets of our solar system register. A planet with a lower than rocky density has something else mixed in, something lighter. The most plausible candidate in this context is water. Not water as a thin veneer on the surface of a rocky world, but water as a substantial fraction of the planet's total mass. Estimates based on the density calculations suggest that TRAPPIST-1f may contain more than 10% water by mass. Earth, by comparison, contains well under 1%. A world with 10% water by mass, at this distance from its star, at these temperatures, would not be a planet with rivers and beaches and shallow seas. It would be something stranger and quieter. The water would not all sit on the surface in gentle liquid form. At the pressures that accumulate at the base of a deep ocean, hundreds of kilometers of water pressing down, ice forms even at temperatures above the nominal freezing point. The physics of water under extreme pressure allows for structures that do not exist in any ocean on Earth. Deep enough, the water would transition into a compressed crystalline form, pressing against whatever rocky mantle lies beneath it. Above that high-pressure ice, a liquid ocean of unknown depth. Above that, perhaps a surface of ice, or vapor, or some layered combination that the planet's atmospheric pressure and temperature balance allows. These are hypothesized structures, built from models that use the density measurement as their starting constraint and let physics follow. They are not confirmed, but the density of TRAPPIST-1f does not fit a rocky world, and the most physically consistent explanation for what it is involves vast quantities of water. A world like this has no precise analog in our solar system. Earth is rocky with a thin surface layer of water. Mars is rocky and dry. The gas giants are enormous envelopes of hydrogen and helium around small cores. But Europa, a moon of Jupiter, offers one image to hold against it: a world with an outer shell of ice covering a subsurface ocean, warming from below through tidal friction and perhaps volcanic heat leaking up from the rocky layers beneath. TRAPPIST-1 FEF, if the density models are correct, may be something related in structure, but planetary in scale, sitting in the weak warmth of a cool star with an ocean that makes Europa's subsurface sea look small. The question of what temperature that ocean might hold, whether the surface above it carries liquid or ice, whether the thin warmth arriving from the star could under any scenario soften the upper layers into something navigable, remains open. No measurement yet taken has resolved it. The seventh planet, TRAPPIST-1G, moves in an orbit just slightly farther out again, completing one circuit of its star every 12.5 Earth days. At that distance, it receives about 26% of Earth's insolation. Its equilibrium temperature, stripped of any atmospheric contribution, settles near 198 Kelvin, roughly 75 degrees below the freezing point of water. That baseline temperature requires substantial greenhouse warming to bridge. The atmosphere would need to trap heat aggressively to lift the surface temperature above freezing, and the range of compositions that could accomplish this, while physically possible, narrows compared to what TRAPPIST-1e and even 1f require. TRAPPIST-1G is the largest of the three temperate worlds. Its radius is estimated near a tenth larger than Earth's. Its mass is estimated near about 1 1/3 times Earth's, though the uncertainty in that number spans a reasonable range above and below. Like TRAPPIST-1F, its bulk density falls below what a purely rocky planet would register, suggesting a composition that incorporates a significant water or volatile fraction. The same class of interior model applies. A deep ocean world, perhaps. A globe of high-pressure ice at its base, giving way to a liquid layer above, capped in turn by a surface of ice or mixed phases, with whatever thin atmosphere the planet has retained, draped above all of it. The outermost of the three temperate planets, receiving only about a quarter of Earth's sunlight, sits near the edge of the zone where any model can place liquid water on the surface. Some models do, under specific combinations of atmospheric thickness and composition, others do not. The consensus view, such as one exists, treats TRAPPIST-1G as a cold world, plausibly warmer than its equilibrium temperature alone would predict, but likely not warm enough at the surface for open liquid water under a broad range of atmospheric scenarios. And yet the water is almost certainly there, not as a surface ocean open to the sky, but locked within the planet's bulk, carrying through its interior in forms that temperature and pressure dictate. If tidal forces, the gravitational flexing that the resonant chain of orbits generates inside each planet as it moves through its slightly elliptical path, contribute any meaningful heat to the interior, the balance shifts. A small addition of heat from below can do what the star's light from above cannot always manage. It widens the range of conditions under which liquid water persists somewhere within the planet's structure. On Europa, tidal heating is believed to keep a substantial ocean liquid beneath kilometers of ice. On TRAPPIST-1G, a world larger and more massive, with a richer reservoir of water by mass, the same mechanism could operate on a grander scale. Whether it does is not yet known. The tidal heating rates for the TRAPPIST-1 planets are estimated from orbital models, and the estimates carry large uncertainties. But the possibility is physically grounded, and it means the interior of TRAPPIST-1G cannot be dismissed simply because its surface sits at the outer margin of the warm zone. The gradient continues outward past these three worlds. And the eighth planet, the last of the 7 known, receives only about 14% of what Earth draws from the Sun. Its equilibrium temperature falls deeper into the cold. Almost all atmospheric models, regardless of the composition they assume, leave its surface frozen. The greenhouse warming required to push the surface above freezing would need to be so extreme, from an atmosphere so thick and so rich in absorbing gases that the planet itself would barely resemble an Earth analog anymore. It would be more like a cold, compressed version of Venus than anything temperate. It occupies a place in the system's architecture that speaks to the outer boundary, the far quiet edge, where warmth from the star becomes so diluted that even generous models find no pathway to standing water at the surface. It is a cold world by every current account, and its distance from the star is the simple physical reason why. But even here, the water need not be absent from the planet entirely. The same low density signature that characterizes the middle and outer planets of the system applies to this world as well, suggesting a volatile rich bulk. The water is probably there, locked inside. The star is simply not enough from this distance to warm the surface above the point where any of it can flow freely. The outermost planet moves in an orbit that takes about 18 3/4 Earth days to complete. In the time it takes a person to finish a working week and a weekend, and a full additional week of ordinary life, this planet completes one full year. That smallness of scale, years measured in days, is one of the most persistent features of this compact system, and it applies to the temperate worlds with the same quiet force. TRAPPIST-1e, the most Earth-like of the three, orbits every 6 1/10 days. Its year is less than a week long, measured in the way Earth measures time. In the span of a single calendar month on Earth, TRAPPIST-1e completes nearly 5 orbits of its star. 5 years, in that planet's reckoning, pass while a person on Earth experiences 1 month of winter or spring. This compression of time is not merely a curiosity of scale. It is a physical consequence of the star's low energy output. Because TRAPPIST-1 produces so little heat compared to the Sun, the only orbits warm enough for liquid water sit extraordinarily close. Close orbits are fast orbits by the mathematics of gravity. The shorter the distance from the star, the stronger the gravitational pull, and the faster a planet must move to maintain its orbit without spiraling inward. The planets of the TRAPPIST-1 system travel around their star at speeds that carry them through their full orbital paths in days rather than the months and years that mark the orbits of the planets in our solar system. For the temperate worlds, this speed, this closeness, this compactness carries implications for the quality of the light arriving at each surface. The star that TRAPPIST-1e orbits is not far away in the way the Sun is far from Earth. At the distance TRAPPIST-1e travels, the star would appear to an observer on the surface, or above it, or at whatever altitude observation might be imagined, as a large reddish-orange shape in the sky, visually larger than the full moon appears from Earth's surface. Though far dimmer than the Sun, the color of the light is the most significant difference. Where the Sun pours energy predominantly in visible wavelengths, in the yellow and white and blue light that eyes evolved to see by, TRAPPIST-1 pours most of its energy in the near infrared, in wavelengths slightly too long for human eyes to register. The light arriving at TRAPPIST-1e's surface would be extraordinarily dim to human vision. Even at midday, if the concept of midday applied, which requires a rotation that may or may not exist on these close orbiting worlds, the amount of visible light reaching the surface would be a small fraction of what Earth receives. The total energy accounting for the infrared would be closer to the 2/3 of Earth's value already discussed. But visible light, the narrow band a human eye is tuned to, would be thin and deep red and quiet. Whether any chemistry that could process that light, any analog to the photosynthesis that green plants use on Earth, could operate under those conditions is a question that opens into biology, into a domain beyond the current boundaries of what the physics and chemistry of the system can confirm or deny. What the physics establishes is that the energy is there and that organisms on Earth already process light across a wide range of frequencies, including wavelengths close to what TRAPPIST-1 produces most abundantly. Some bacteria on Earth use near-infrared light for photosynthesis. The range of what is biochemically possible under reddish dim starlight is not zero, it is an open interval, bounded on one end by physics and on the other by something that has not yet been investigated from 40 light years away. The habitable zone, defined in these broad terms of energy received and water theoretically liquid, holds 3 of the 7 worlds in a corridor that spans only a few million kilometers in total width. The distance from the inner edge of that corridor to the outer edge is smaller than the distance from Earth to the Moon, measured in absolute terms. These 3 temperate planets, the 5th, the 6th, the 7th, move in orbits so close to one another that they could be lined up end to end, and together they would still not span the distance separating the innermost and outermost planets of our own solar system. Everything meaningful in the TRAPPIST-1 system is packed into a space that, by the measures of our own planetary neighborhood, is almost unimaginably tight. 3 worlds with the physical prerequisites of water, warmth, rocky or water-rich composition, and orbits in the correct range, all contained in a band of space narrower than the gap between Earth and Moon. The contrast between this compactness and the timescales involved is one of the most difficult things to hold in mind simultaneously. These 3 small, closely orbiting worlds have been moving in their current paths, if models of the system's age are correct, for somewhere between 7 and 10 billion years. That is almost twice the age of Earth. The orbits have been stable, the resonant chain has been maintained, the star has continued to shine, and these 3 worlds have been receiving, for a span of time longer than the entire age of our solar system, the same fractional warmth from the same dim reddish star. What that warmth has done to whatever materials are present on their surfaces over 7 to 10 billion years cannot be stated with certainty. It can only be noted that the timescale is vast, that chemistry operating under stable conditions over billions of years has produced remarkable things on at least one world known, and that the conditions present in this narrow temperate band are not, on the basis of current physics, excluded from producing something analogous. That restraint, the measured and honest acknowledgement that conditions are plausible rather than confirmed, that evidence is physical rather than biological, that possibility is not probability, is the register in which this system is best understood. The habitable zone is a definition built from physics. The planets within it are real, with measured radii and estimated masses and calculated densities. The question of whether any of them bears the further stranger category of life belongs to a longer investigation that current instruments are only beginning to reach toward. In the meantime, there is something quietly substantial about simply understanding what these worlds are in purely physical terms. TRAPPIST-1e, roughly 9/10 the size of Earth, receiving 2/3 of Earth's warmth, turning in an orbit 6 days long around a star the color of cooling iron. TRAPPIST-1f, denser with water than any inner planet, receiving a little more than 1/3 of Earth's energy, a world that may carry within itself an ocean larger and deeper than anything on Earth, sealed beneath ice and sustained by the slow tidal warmth of gravitational motion. TRAPPIST-1g, the largest of the 3, sitting at the outer margin of warmth, cold at its equilibrium, possibly warmer than that in its interior. A planet whose bulk composition speaks of abundant water that the surface temperature alone cannot express as a liquid ocean open to any sky. Three temperate worlds, three sets of physical parameters, three different answers to the same question of what warmth does to a planet when the star providing it is dim and close and ancient. The question of water underlies all three. Water is not a mere ingredient in the habitable zone calculation. It is the specific molecule whose phase transitions, solid, liquid, gas, mark the boundaries of the zone itself. The reason the habitable zone is defined as it is comes down entirely to the behavior of water across a temperature range. Liquid water, specifically, and the narrow thermal band in which it persists at pressures typical of a planetary surface. Too little energy, ice. Too much vapor that escapes into space. In between, the range where water flows, where it cycles, where it interacts with rock and atmosphere, and whatever chemistry a surface supports. The three temperate planets of TRAPPIST-1 orbit in or near that range. Two of them almost certainly contain water in bulk quantities, buried in their interiors. Whether any of it reaches the surface as a liquid depends on atmospheric conditions. No telescope yet built can fully characterize. The James Webb Space Telescope, the most capable instrument humans have yet aimed at the sky, has begun gathering transmission spectra from the inner TRAPPIST-1 planets. Those measurements look at starlight filtered through a planet's atmosphere during a transit, seeking the spectral fingerprints of specific molecules. The early results for the innermost worlds lean toward planets without substantial atmospheres, though the uncertainties remain significant and the interpretations are ongoing. The habitable zone planets, the three at the heart of this discussion, represent the next phase of that investigation. Their transmission spectra would require more observation time, more careful stacking of data, more patience from the telescopes and the people operating them. That investigation is underway. No confirmed atmospheric detection for any of the three temperate worlds has been announced as of the current state of knowledge, and what the spectra will ultimately reveal is genuinely open. The patience that the investigation requires mirrors something in the star itself. TRAPPIST-1, burning slowly, conserving its hydrogen with a parsimony our own sun does not practice, will continue to provide exactly this warmth to exactly these three worlds for trillions of years. The habitable zone will not shift appreciably for timescales, so long they exceed the current age of the universe by a factor of 1,000. The temperate corridor around this star is a stable, enduring feature of the system, not a fleeting phase, not a brief window, but a permanent geographic fact of this tiny solar neighborhood, measured in units of cosmic time that make the span of human history seem as brief as a single breath. The energy gradient continues to diminish as the star falls behind. The outermost planet turns in its slow, cold orbit. Each world, in turn, receives its share of the faint reddish warmth. TRAPPIST-1e turns. TRAPPIST-1f turns. TRAPPIST-1g, at the farthest edge of the temperate band, moves through its orbit in 12.5 quiet days, receiving just over a quarter of what Earth draws from the Sun, enough in the right conditions to matter, enough at the very least to keep the question open. Beyond TRAPPIST-1g, the eighth planet moves in its wide, cold arc. Even farther out in the same orbital plane, there is nothing else measured and confirmed, only the star's warmth continuing to diminish with the square of distance, as the physics of energy always dictates. The last of the 7 worlds at the outer edge of the known family receives its 14% of Earth's insolation. It takes it in, it radiates most of it back. Its surface, by any current estimate, lies beneath ice, quiet and still. The light that reaches it from the star is weaker than the light that falls on any of the temperate worlds. It is redder. It carries less energy per photon. It arrives, even at this short distance in astronomical terms, as a faint and cooling gift from a star that is itself the dimmest kind of thing that can still be called a star. And yet it arrives, steadily. It has been arriving for billions of years. It will continue to arrive at this same low level without perceptible change for billions more, and then for trillions more beyond that. The outermost world does not warm. Its surface holds the cold that space provides by default, the temperature that a rock reaches when the energy falling on it from a dim and distant source is only barely more than nothing. The ice there, if ice it is, has been ice for as long as the system has existed in its current form, and in the absence of any heat source sufficient to change it, it will remain ice for the full remainder of the star's life, a span of time so long that the geology of ice itself becomes a form of permanence, as settled and unchanging as the stone beneath it. That cold, patient world at the outer edge holds its orbit. It does not speak of any answer. It simply marks the boundary where the warmth runs out, and beyond which the darkness returns to full authority, and the question of water and heat and what they might produce together becomes, for the time being, one that the physics has set aside. The three temperate worlds remain where they have always been, orbiting in their narrow band, receiving their careful fractions of a slow star's patient light, holding whatever water they contain in whatever form the pressure and temperature of each interior demands, turning in silence without urgency around a dim reddish ember that will still be burning long after the present age of stars has passed into a memory held only by the universe itself. On a world that orbits close enough to its star that the star never moves, gravity has done something that takes a long time to understand. It has stopped the planets turning, not all at once and not quickly. Over millions of years, the tidal pull of the star reached into the planet's interior and slowed its rotation, degree by degree, the way a hand pressed gently against a spinning wheel will eventually bring it to rest. And then the planet held still, one face toward the star, one face away, the same ground, the same sky, the same light or darkness, held in that position for longer than the earth has existed. The star hangs fixed. It does not rise. It does not arc or wheel or set. It occupies a single point in the sky. A reddish-orange glow, smaller than the sun, appears from Earth but far closer than it looks, radiating in wavelengths that lean toward heat rather than sight. Below it, directly below, the surface receives that light without pause. The rock heats. The air above the rock rises, and it has been rising for a very long time. This is what tidal locking does to a world. It divides it. The term itself, tidal locking, describes a gravitational process, the same family of forces that holds the moon's near side always facing Earth, that has slowed the rotation of many small bodies close to large ones throughout the solar system. When a planet orbits very close to its star, the star's gravity pulls slightly harder on the near side of the planet than on the far side, stretching the planet by a fraction, raising tidal bulges in the rock the way the moon raises bulges in Earth's oceans. If the planet spins faster than it orbits, those bulges lag behind, and the star's gravity tugs at them, gradually breaking the rotation. The braking continues until the spin and the orbit match exactly, one rotation per orbit. The bulge now points permanently toward the star, and the dragging stops. The planet is locked. For all 7 worlds circling TRAPPIST-1, the orbital periods are short. The innermost completes a full circuit in 1.5 Earth days. Even the outermost takes fewer than 19. At those distances, so close to even a dim star, the tidal forces are strong, and the timescales for locking are short on geological terms, a few 100 million years at most for the inner planets, perhaps a billion for the outermost. Against a star that is estimated to be between 7 and 10 billion years old, there has been time, and more than enough time, for every one of these worlds to stop turning. So picture each of them still, each one with a hemisphere that has not known darkness since the locking was complete, each one with a hemisphere that has not known light. The day side of a tidally locked planet is not quite like anything in the inner solar system. The nearest comparison is Venus, a world hot enough to melt lead, where the thick atmosphere has spread that heat more evenly, but on a tidally locked planet with a thinner atmosphere, the distinction between the lit and dark sides is far more extreme. On the day side, directly beneath the star, the ground receives a constant bath of energy. The temperature climbs. In the models, the substellar point, the single spot on the ground where the star is directly overhead, is the hottest place on the planet. Heat radiates upward from the rock, from whatever liquid or solid surface lies there, and the air begins to move. The night side is something else entirely. Without circulation, without any mechanism to carry warmth from the lit face to the dark one, the night side of a tidally locked planet would cool toward temperatures that approach those of deep space. The rock would radiate away the last of its heat into the void overhead. Gases in the atmosphere would eventually freeze and settle out. The darkness would not be the darkness of a night sky, where the stars are visible and the air holds the memory of the day's warmth. It would be a geological darkness, a permanent condition of the terrain. Ice would coat surfaces that had never seen light and would never see it. The cold would be patient and absolute, but atmospheres complicate everything. And here, in the difference between a world with no atmosphere and a world with even a thin one, the entire question of these planets resolves or remains open. Air moves. Even a modest atmosphere, a layer of gas only a fraction of Earth's own, can carry heat from one side of a planet to the other. The mechanism runs like this. On the day side, the air is warmed. Warm air is less dense than cold air. It rises. High in the atmosphere, above most of the mass of the gas column, it spreads outward from the substellar point in all directions, carried by the pressure gradient, flowing from where there is too much warmth and too much pressure toward where there is too little. It crosses the terminator, the boundary line between day and night, and flows onto the night side. There, it cools. The heat that the planet carried from the lit surface radiates away into space. The cooled air descends. On the night side surface, it flows back along the ground, across the terminator, drawn toward the day side by the low pressure left behind as warm air keeps rising. A full circuit, planet-spanning, continuous, and driven entirely by the unequal heating of one side by a star. This circulation does not operate like weather on Earth, where the pattern shifts and varies, where high-pressure systems drift and trade winds change with season. On a tidally locked world, the driver of the circulation is fixed. The day side is always here. The night side is always there. The rising column of warm air, directly beneath the star, is a permanent feature of the climate system. The descending air on the night side is equally permanent. The circulation cells that connect to them, imagined as slow, vast breathing, warm breath out from the day and cold breath returning along the ground, would repeat without pause for as long as the planet holds its atmosphere. In the best models, this circulation can carry enough heat to prevent the night side from freezing so thoroughly that atmospheric gases condense out and collapse. For the habitable zone planets, the ones whose size and distance from the star make liquid water plausible, this is not a small detail. A planet that loses its atmosphere to nightside freeze-out loses the atmospheric pressure that keeps water liquid on its surface. The entire question of whether these worlds can support standing water depends in part on whether their circulation systems are robust enough to keep the nightside air above the condensation points of the major atmospheric gases. No one is sure whether they are. The circulation models give a range of answers, and the answer in any particular case depends heavily on what the atmosphere is made of, how thick it is, and how active the star has been over geological time. All three of those things are uncertain for the TRAPPIST-1 planets. What the models do confirm is that the basic physics of the circulation is real, that tidally locked planets are not necessarily the dead, frozen on one side worlds they were once assumed to be, and that a planet with a moderate atmosphere and the right composition could maintain surface temperatures that vary between the hemispheres by tens of degrees rather than hundreds. And on a world where the difference between liquid water and a frozen wasteland may be a matter of 30 or 40 degrees, that is not a small range to work within. TRAPPIST-1 is an old star, and old stars carry history. This one has been burning for somewhere between 7 and 10 billion years, longer than our solar system has existed, long enough that whatever the planets were like in their youth is not necessarily what they are now. And in their youth, the planets faced something that is easier to survive in the present than it was in the past. Ultra-cool dwarf stars like TRAPPIST-1 are active. They flare. A stellar flare is a sudden eruption of energy from the star's surface, a release of magnetic energy that is built up in the stellar atmosphere, unleashing a burst of radiation and charged particles that briefly overwhelms the star's ordinary output. For a brief period, the flare can raise the star's emission of extreme ultraviolet and X-ray radiation by orders of magnitude. On a planet close enough to be in TRAPPIST-1's habitable zone, this burst arrives in minutes, washing over the atmosphere, depositing high-energy photons into the upper gas layers. TRAPPIST-1 flares frequently, more frequently, in fact, than our own sun, and with greater effect relative to the planet's distances. The energy arriving at the habitable zone planets during a large flare can be many times the ordinary stellar flux, a sudden violent brightening in wavelengths the planets would not otherwise receive in such quantity. Over geological time, the models suggest that TRAPPIST-1's planets may have received hundreds of times more extreme ultraviolet radiation than Earth has received from the Sun across equivalent spans. That radiation does not simply strike the planet's surface. The upper layers of an atmosphere absorb it. The energy strips electrons from gas molecules, a process called photoionization, which breaks molecular bonds and can excite gas particles to speeds above the planet's escape velocity. Particle by particle, over long timescales, a process called atmospheric sputtering can erode the upper atmosphere. The lost gas drifts away into space. If it is not replenished, the atmosphere thins, and a thinner atmosphere means less protection, which means more erosion, which means a thinner atmosphere still. In the early life of the TRAPPIST-1 planets, when the star was younger and almost certainly more active than it is now, this erosion could have been severe. The inner planets, the ones closest to the star, receiving the strongest radiation at the shortest distances, faced the harshest early conditions. What atmospheres they had at formation, whatever volatile envelopes came with the raw material of their construction, were subjected to the full force of a young, active, flaring star for hundreds of millions of years. Whether anything survived that era depends on factors that remain uncertain. A planet with a strong magnetic field, generated by a convecting conducting interior, similar to the dynamo inside Earth, can deflect some of the charged particles that accompany flares. The planet's magnetic field lines funnel the incoming particles toward the poles rather than letting them strike the atmosphere directly. Earth's magnetic field does something similar, producing the auroras at high latitudes as a byproduct of the deflection. For the TRAPPIST-1 planets, whether they have magnetic fields of comparable strength is unknown. Their interiors are not directly observed. The presence or absence of an internal dynamo depends on composition, cooling history, and tidal heating, all of which are constrained only loosely by current measurements. A planet can also replenish what it loses. Volcanic outgassing, the release of gases from the planetary interior through eruption and through slower diffuse seepage, can gradually rebuild an eroded atmosphere. Earth has done this repeatedly across its history, its volcanic systems releasing carbon dioxide, water vapor, sulfur compounds, and other gases that have contributed to the atmospheric composition over billions of years. If the TRAPPIST-1 planets have active volcanic interiors, and the gravitational interactions in the resonance system may provide enough tidal heating to sustain volcanism on some of them, then outgassing could offset at least a portion of the atmospheric loss to flaring. The full accounting of atmosphere gained and atmosphere lost across billions of years of flaring and outgassing and magnetic shielding is a calculation that no current model can make precisely. The honest picture is one of deep uncertainty about whether the habitable zone planets of TRAPPIST-1 have retained atmospheres at all, let alone the particular compositions that would make surface liquid water plausible, but they may have. That is the quiet, open fact at the center of the system's scientific interest. The range of possible atmospheric compositions that the models consider spans something like the full variety of rocky planet atmospheres seen in this solar system, and then further, on one end, a thin carbon dioxide atmosphere, something like what Mars has now, only 1/100th the pressure of Earth's air, cold, offering almost no greenhouse warming, leaving the surface exposed to most of the flare radiation, and reeking like the Decussi, one coven fortal, the Subidi Haute Mole. On the other end, a thick Venus-like greenhouse atmosphere, dense with carbon dioxide and perhaps sulfuric acid clouds, where the pressure at the surface would be many times Earth's, and the temperature beneath the cloud deck could be extreme. Somewhere between, in the models, lies an atmosphere like Earth's, dominated by nitrogen, with moderate amounts of carbon dioxide and water vapor, providing a greenhouse warming of perhaps 30 or 40 degrees above the bare equilibrium temperature, and shielding the surface effectively from most radiation. For the habitable zone planets of TRAPPIST-1, that Earth-like middle scenario is the one that would permit liquid water at the surface. It is not assured. It is not ruled out. The science sits in that space, not on either side of the answer, but in the gap between knowing and not knowing, which is where much of the most interesting science lives. And in that gap, it is worth spending time with what such a planet might feel like, in purely physical terms, if the conditions are favorable. Consider a world where the atmosphere has held a nitrogen-rich envelope, modest in greenhouse warming, enough to carry heat from the day side toward the night without the catastrophic freeze-out of the major atmospheric components. The star overhead, fixed reddish-orange, smaller than the sun, appears from Earth, bathes the day side in light that is heavy in near-infrared wavelengths, the kind of light that warms things without being particularly bright to eyes adapted to look for blue-green visible wavelengths. The substellar point is warm, not scorching. The star is dim by solar standards, but warm in the way that an afternoon in autumn feels warm, a steady low heat without intensity. The wind begins at the ground and rises. Beneath the fixed star, the heated air lifts in a broad column, slow and continuous, carrying heat upward. At altitude, the column spreads, flowing outward in all directions. It crosses the terminator line, the boundary that on this world is not a moving shadow, but a permanent geographic feature, a ring of perpetual twilight, where the star sits always at the horizon, its light always arriving at a shallow angle, always casting long shadows across whatever terrain lies at that latitude. In the terminator region, the light is the color of a long sunset. The star rides the horizon, half above and half below, never rising higher and never setting. The air at the terminator is cooler than on the day side and warmer than on the night side, and it moves. The high altitude flow overhead pushes toward the night, while the surface level return flow pulls toward the day. The terminator is not a boundary so much as a corridor. A long, slow current of air passes through it in both directions simultaneously, at different heights. On the night side, the returning air descends. The heat it carried from the day side radiates away over time, and the air cools as it settles toward the ground. The surface is cold and dark. The star is below every horizon. There are no shadows because there is no light source. The sky above the night side shows stars, many more of them perhaps than any of the sky's other regions, because there is no nearby bright source to wash them out, only the faint glow of the galaxy and the distant points of other suns. And somewhere in that sky, our own sun would be one of those points, a star among stars, unremarkable in brightness, in the direction of Aquarius, as seen from that world's southern hemisphere. Beneath the night-side sky, the air keeps moving, not still, not dead, but carrying the circulation on its slow circuit, the return flow at the surface, moving across frozen or frigid terrain toward the warmth it cannot quite feel yet, drawn by the pressure gradient that the dayside heating maintains continuously without pause. Near the substellar point, the model suggests something else might happen, where the incoming starlight is most concentrated, where the surface temperature climbs highest. The rising air column carries water vapor upward. At altitude, where the air is colder, that water vapor condenses. Clouds form. In the models for certain atmospheric compositions and pressures, a permanent cloud bank develops directly beneath the star, hovering at the substellar point, a thick white cap of water ice crystals or liquid droplets. It reflects a portion of the incoming starlight back into space, which means the surface beneath it receives less energy than it would if the cloud were absent. This cloud acts as a thermostat of sorts. The hotter the surface, the more evaporation, the more cloud, the more reflection, the less heat reaching the ground. The system self-limits, not by design, not with any intention, simply because the physics of water and air and light in those conditions produces that outcome. In Sprig, whether this cloud bank is thick enough and stable enough to be a meaningful climate regulator, or whether it breaks apart in the complex three-dimensional reality of a moving atmosphere, is something the models disagree on. The answer depends on details of atmospheric chemistry and dynamics that the current observations of the TRAPPIST-1 system cannot constrain. The cloud is real in the models. Whether it is real on any of the planets themselves is another open door. What all of this means, taken together, is that the climate systems of the TRAPPIST-1 habitable zone planets are not simple, not uniform, and not predictable from first principles alone. They are systems of interacting processes: stellar heating, atmospheric circulation, cloud formation, flare exposure, magnetic shielding, volcanic replenishment, each one influencing the others, each one operating across timescales ranging from days to billions of years. The planets sit at the intersection of all of them. The surface conditions that result are not determined by any single factor, but by the slow competition and balance among all these forces acting together, and that is not so different from Earth. Earth's climate is also a system of interacting processes: ocean currents, atmospheric circulation, ice albedo feedbacks, volcanic outgassing, biological modification of the atmosphere. The difference is that on Earth we have the full record, or most of it, available to read in rock and ice and ocean sediment. For the TRAPPIST-1 planets, we have the physics, and we have the constraints that distant observations can provide, and we have models. The models are good. They are not complete. There is a quality of stillness that comes with imagining these climate systems in operation. Not the stillness of things that are not happening, but the stillness of things that have been happening continuously for so long that the rate of change is imperceptible on any human timescale. The winds that blow from the day side to the night side on a tidally locked planet have been blowing, if the atmosphere has held, for billions of years. The cloud at the substellar point, if it exists, has been forming and dissipating and reforming across a span of time that is difficult to place beside any human reference. The Terminator's long twilight has not changed its position since the planet stopped turning. There is something in that permanence that is different from weather on Earth, where the storms are transient and the seasons turn and the winds shift. On these worlds, the climate is the landscape. It does not pass through. It stays. And TRAPPIST-1 itself, smaller than any star can ordinarily be called, cooler than most things the human mind associates with fire, keeps burning. Its surface radiates in deep red and near infrared, the light spreading outward in all directions, diminishing with distance, reaching its 7 planets in amounts scaled by their proximity. The innermost worlds receive a fierce flux, the outermost worlds receive only a trickle, and all of them face it without turning, their one permanent side absorbing whatever the star offers, their other side held in the dark. The star also flares. It has always flared. In the early period of the system's history, when the star was young, it was more magnetically active than it is now, flaring more often and more intensely, washing the planets in high-energy radiation at rates that would have been lethal to any unprotected surface chemistry resembling life. As the star aged, the activity diminished. Old red dwarfs flare less vigorously than young ones, but even now, TRAPPIST-1 produces flares at a rate that keeps the radiation environment of its planets elevated above what Earth experiences from the Sun. The planets have had billions of years to adapt, if adaptation is the right word for a geological process, or to be stripped bare by what they could not deflect. The magnetic field question matters here, in a way that is quietly central to the whole picture. A planet without a strong magnetic field orbiting a flaring star at close range faces a difficult long-term situation. The extreme ultraviolet and X-ray bursts of a large flare arrive and deposit their energy in the upper atmosphere. If the atmosphere is ionized efficiently enough, and if the planet's escape velocity is low enough, the heated gas at the top of the atmosphere can reach speeds that carry it away permanently. A planet with a strong magnetic field can divert the charged particles before they deposit energy in the gas. Not perfectly, not completely, but enough to change the rate of loss significantly. Over 1 billion years, That rate difference can be the difference between an atmosphere and its absence. For Earth-mass planets, and most of the TRAPPIST-1 worlds fall close to Earth in mass, within a factor of 2 or so, the question of whether a magnetic field is maintained comes down to the thermal state of the interior. A planet with a molten iron core convecting vigorously enough to generate a self-sustaining dynamo will have a magnetic field. A planet whose core has cooled and solidified, or whose interior is composed differently, may not. Mars lost its magnetic field long ago, and it is not a coincidence that Mars also lost most of its atmosphere. The comparison is not exact. Mars is smaller than Earth, and its lower gravity made atmospheric escape easier regardless of magnetic protection, but it illustrates the principle. For the TRAPPIST-1 planets, the tidal interactions within the resonant chain may provide enough heat to keep interiors active for timescales longer than purely internal processes would sustain. A planet being continuously flexed by the gravitational pulls of its neighbors generates heat in its interior through friction. That heat supplements the original heat of formation and the heat from radioactive decay within the rock. If the extra heat is sufficient to maintain a convecting liquid iron region in the core, the magnetic dynamo persists, the field is maintained, and the atmosphere has a defender. If not, if the tidal heating is insufficient, or if the planet's composition does not produce a suitable core, the field weakens, the flares score deeper, and the atmosphere retreats over geological time. The models do not fully resolve this. The tidal heating estimates for the TRAPPIST-1 planets are uncertain because they depend on internal structure parameters, particularly a quantity called the tidal quality factor, which describes how readily a planet's interior dissipates tidal energy as heat that cannot currently be measured directly. The estimates span a wide range. For some scenarios, the inner planets receive enough tidal heating to maintain active interiors and magnetic fields. For others, they do not. The uncertainty is real, and acknowledging it is part of the honest account of what is known. What can be said with more confidence is that the resonant chain itself, the synchronized orbital arrangement that keeps the planets in their precise gravitational relationship, has shaped the interior histories of these worlds in ways that purely isolated planets would not experience. The resonance means the planets have always been pulling on one another. The ellipticities it maintains in their orbits mean the tidal flexing has been continuous. The system is not a collection of 7 independent worlds. It is a family, and the members of the family have been affecting each other for as long as the resonance has held. That interconnection extends even to the atmospheres. In one sense, when a large flare erupts from TRAPPIST-1, all 7 planets receive it. The time delays are small. At these distances, even the outermost planet is reached within a few minutes of the innermost. A single flare event is a system-wide event. If it is large enough to strip gas from the uppermost atmosphere of the innermost worlds, it is also washing over the habitable zone planets simultaneously, depositing energy in their upper atmospheric layers, driving chemistry and erosion and heating in parallel. The flare passes. The star returns to its baseline dim red glow. The atmospheres, whatever remains of them, settle back into their equilibrium circulation patterns. The wind resumes its slow crossing from day to night. The cloud at the substellar point, if it is there, continues forming. The night-side cold continues. The terminator's twilight continues. That long ring of permanent sunrise and sunset, where the light arrives forever at an angle and the horizon holds the star in place, neither rising nor descending. Stand long enough in imagination at the terminator, and the strangeness of the place begins to give way to something more like familiarity. The light is red and dim, arriving from a source fixed at the horizon. The air moves with a persistence and directionality that weather on Earth does not sustain. The ground underfoot, rock, presumably, or ice, or some layered mixture of the two, has been subjected to this same light at this same angle for longer than the Earth's mountains have existed. The wind that moves past has been moving in this same direction for longer than any geological feature on Earth has held its shape. In that permanence, there is a kind of peace, not the peace of something frozen or dead, but the peace of something ongoing, a process so old and so continuous that change is not its character. The wind blows, the star holds still. The circulation carries its load from one side of the world to the other, and does not stop, and has not stopped, and will not stop as long as the atmosphere remains and the star keeps burning, and TRAPPIST-1 will keep burning for a very long time. Its dim red fire, fed by the slow fusion of hydrogen in its core, runs so economically that the star's expected lifetime stretches into the trillions of years, a time span so far beyond the current age of the universe that most of what exists today will have changed beyond recognition before the star exhausts its fuel. Long after the sun has expanded and dimmed, long after the solar system has changed beyond recognition, TRAPPIST-1 will still be at the center of its compact family of 7 worlds, still delivering its patient reddish light, still driving the wind from day to night on whatever remains of the atmospheres of those planets. Whether those atmospheres hold, whether the warmth reaches the dark sides of the temperate worlds in sufficient quantity, whether water moves, or once moved, across surfaces 40 light-years from here. These are questions that the physics leaves open and that the observations available now have not yet resolved. The answers are there, written into the rock and air and magnetic fields of the planets themselves, and waiting, as such things do, with no particular urgency, for the instruments and the patience required to read them. In the meantime, the wind blows from the day side toward the night, across terminator regions held in permanent twilight, along surfaces that have known only their single, unchanging condition for longer than memory can hold. The star does not set, the night does not end. The circulation continues, vast and slow and patient, moving warmth across the face of a world that has learned, in its own geological way, to live between light and dark. From the timing of a shadow, the inside of a world can be read, not the shadow itself. No telescope sees it fall. What the instruments record is a dimming, a fraction of starlight gently withheld, a number dropping by a precise amount for a precise duration before the star returns to full brightness. From that dimming comes the radius of a world. From the radius comes a volume, and when the mass arrives through a separate, slower method, through the patient comparison of each planet's timing against all the others, the radius and the mass are placed beside each other, and what emerges is a density, a single number, the weight of a world divided by its size. And from that number, read carefully and compared against the known densities of rock and water and iron, an interior begins to take shape, not seen, not visited, inferred with quiet confidence from the behavior of light on a star 40 light-years away. This is how the insides of the TRAPPIST-1 planets were first understood, not by any probe descending through cloud, not by any drill pressing into crust, but by the patient arithmetic of light and time. The innermost worlds, TRAPPIST-1 bed and 1c, come back dense. Their radii are small, and their masses are substantial enough that when the calculation is complete, the result points toward rock, silicate rock, the kind that makes up the bulk of the Earth and the Moon and Mars, iron and magnesium and silicon, pressed into spheres by their own gravity. Their densities broadly match the kind of composition a person would recognize from the inside of any terrestrial planet in this solar system. The rock may differ in detail, the ratio of iron to silicate may shift, but the broad category holds. These are stone worlds, compact and solid, their interiors dense all the way through. The outermost worlds tell a different story. TRAPPIST-1 Fef, 1G, and 1H arrive at densities too low for pure rock. If they were simply stone all the way down, they would be heavier than they are. Something is lightening them. Something with a lower density than silicate is present in large enough quantities to pull the average down, and the most plausible candidate, given their position in the system, their distance from the star, and the temperatures likely to prevail at their orbits, is water, not a thin film, not the few kilometers of ocean that coat roughly 2/3 of the Earth's surface. Something far more substantial. Scientists estimate that these outer planets may carry water fractions exceeding 1/10 of their total mass, and possibly more. On Earth, water makes up roughly a fraction of a percent of the planet's mass. On these worlds, it may be hundreds of times more abundant, by proportion, than it is here. An ocean 10% of a planet's mass is not an ocean in any familiar sense. It would not sit at the surface like a blue skin, at the pressures generated by so much water pressing down on itself. The water at depth would pass through phase transitions, states that do not occur on Earth's ocean floor, and become forms of ice that exist only under extreme compression, dense crystalline structures that are still water, chemically, but bear no resemblance to anything that forms in a winter sky. Below the liquid layer, if there is a liquid layer, there would be ice. Not the cold surface ice of a frozen lake, but high-pressure ice at the base of a column of water hundreds of kilometers deep, a floor made of a substance the body cannot easily imagine. Water, frozen, but hot. This structure, ice below, ocean above, ice or vapor above that, has a parallel in this solar system in the moons of the outer planets. Europa carries a liquid ocean beneath a shell of ice. Enceladus carries one too, and sends it fountaining into space through cracks in its southern pole. These are not hypothetical constructs. They are measured, confirmed, visited by spacecraft that detected their magnetic signatures and tasted their plumes. The outer TRAPPIST planets may be analogues of these moons, scaled up to planetary mass, moved inward to a red dwarf's narrow habitable ring, and set in motion around a star that burns in wavelengths the eye cannot see. The mass of each planet arrived through a method called transit timing variation. It is a slow, intricate kind of listening. When a planet in a multi-planet system crosses its star, it does not always cross at precisely the moment a simple two-body calculation would predict. The other planets are there, their gravity pulling at it, nudging it slightly ahead of or behind its expected position. The deviations are small, often only minutes, sometimes seconds, but across many transits, carefully measured and compared, those deviations accumulate into a signal. The signal carries the masses of the planets encoded in it, the way a piece of music carries information about the instrument that played it. The astronomers who worked through those transit timing variations for the TRAPPIST-1 system assembled years of observations from multiple telescopes, ground-based and orbital, and from the patient comparison of thousands of transit times built a picture of 7 masses, each uncertain by a few percent, each constrained by the behavior of all the others. TRAPPIST-1d is the lightest of the 7. Its mass sits near a third of the Earth's. It is a small world by any measure, and its density places it in an ambiguous zone. It could be a rocky planet with a thin volatile envelope, or it could carry a meaningful fraction of water beneath its surface. It orbits close enough to the star to receive substantial energy, which complicates the water picture. At that distance, water may be in the atmosphere rather than on the surface, held as vapor in a thick envelope rather than pooled in liquid form. The planet occupies a position where the questions multiply rather than resolve, and where honest science holds the answer loosely without forcing it. TRAPPIST-1b is the most massive of the seven. Its mass comes back near 1 1/3 times Earth's, and combined with its radius, the density points toward a rocky, potentially iron-rich interior, a world more like a heavy stone than a water-wrapped one. It sits closest to the star, receiving more than 4 times the energy Earth receives from the Sun. Whatever surface it has is almost certainly too hot for standing water, and the composition of its interior, dense and compact, belongs to an environment shaped by proximity to heat. Between the innermost and outermost worlds, TRAPPIST-1e occupies a place that consistently draws the attention of those who study the system. Its radius is close to 9/10 of Earth's. Its mass, derived from those careful timing measurements, falls near 7/10 of Earth's. The density is consistent with a rocky composition, possibly with a modest water or volatile component, but nothing like the thick water fractions of the outer planets. And its surface gravity, the pull a person would feel standing on its surface, works out to roughly 93% of Earth's own. That number carries its own kind of quiet weight. Among all the planets found beyond this solar system, among the thousands cataloged and characterized to varying degrees of precision, very few return a surface gravity this close to the one in which every living thing on Earth evolved. The body would not need to adapt to it in any dramatic way. Objects would fall at nearly the familiar rate. Bones shaped by a lifetime on Earth would carry their load without strain. It would not feel alien in the way gravity feels alien to astronauts on the moon, where a person weighs less than 1/7 of their Earth mass, and every step is a slow arc. It would feel, if anything, almost ordinary. This is what the density measurements yield. In the end, not certainty, but specificity. Not a confirmed world, but a well-constrained sketch. And from that sketch, with care and restraint, something like a picture of an interior begins to assemble itself. Beneath any surface TRAPPIST-1e might possess, the planet's interior can be imagined in broad layers. The outermost shell is whatever crust the planet has built and maintained, rock cooled from below, bearing whatever scars 4 or more billion years of geological activity have left. Below that, a mantle, silicate rock under pressure and heat, slowly deforming over millions of years, carrying heat from the interior upward by the slow circulation of solid rock that behaves over geological time something like a very thick liquid, and at the center, possibly an iron core, though the planet's lower mass relative to Earth means the pressures at its center are lower, and the conditions for core formation and dynamics differ from what the Earth's own deep interior looks like. None of this is directly visible. None of it ever will be, not with any instrument currently planned or foreseeable. The inference rests entirely on the density, on the analogy with known planetary bodies, and on the physical principles that govern how matter behaves under pressure. What lies at the center of TRAPPIST-1e is a question that instruments answer with probabilities rather than images. But the outer planets hold a version of this question that carries even more weight. On TRAPPIST-1e and 1h, the low densities point toward water fractions that would place liquid oceans if liquid zones exist, at depths and scales without any true parallel in the inner solar system. Imagine the deepest trench on Earth's ocean floor, roughly 7 miles below the surface, the Challenger Deep, a narrow groove in the Pacific where the pressure is more than 1,000 times the pressure at sea level. Now imagine an ocean not 7 miles deep, but hundreds of miles deep. The water at its base would be compressed into forms that do not exist on Earth naturally. The pressure would be immense, and somewhere in that column of water, at some depth where temperature and pressure intersect correctly, liquid might exist, an ocean sealed on all sides, untouched by starlight, unknown to any surface, existing in complete and permanent darkness. The heat that might keep such an ocean liquid does not need to come from above. On the outer TRAPPIST worlds, stellar radiation is faint. TRAPPIST-1e receives only about 14% of the energy Earth draws from the Sun. Even TRAPPIST-1g receives only roughly a quarter. If the surface of these worlds is dominated by ice, and most models suggest it would be, very little of that dim starlight penetrates inward to warm anything below. The heat, if there is heat enough to sustain liquid, must come from inside. There are two sources. The first is radiogenic heat, the slow decay of radioactive isotopes locked in the rock of the planet's interior. Uranium, thorium, potassium, these elements were present in the cloud of gas and dust from which the TRAPPIST-1 system formed, just as they were present in the cloud that formed this solar system. They decay at predictable rates, releasing energy as they go, warming the rock around them. The Earth is still warm partly because of this, its interior heated not only by the energy of its formation, but by the ongoing decay of isotopes that have been counting down since before the planet existed. The TRAPPIST worlds would carry the same inheritance. The system is estimated to be older than this solar system, between 7 and 10 billion years old, which means more of the short-lived radiogenic heat has dissipated, but the long-lived isotopes persist and continue their slow work. The second source is tidal. The TRAPPIST-1 planets orbit in a resonant chain, their periods locked in precise ratios to one another, their gravitational voices pulling at each other in a rhythm that has repeated for billions of years. This resonance maintains slight orbital eccentricities, not large ones, but enough. A planet moving through a slightly elliptical orbit does not travel at a perfectly constant distance from its star, and it does not receive perfectly constant gravitational pulls from its neighbors. It is kneaded, very slightly, as it moves. The rock flexes. The flexing generates heat through friction, the same way a piece of metal warms when it is bent repeatedly, the same way the hands warm when pressed together. This tidal heating is not large for most of the TRAPPIST worlds, but it is not nothing, and for the outer planets where stellar energy is sparse, it represents a meaningful supplement to the radiogenic warmth rising through the rock. Jupiter's moon Io is the most volcanically active body in the solar system, not because of heat from the sun. Jupiter's moons are cold, but because of tidal flexing from Jupiter's immense gravity, and the orbital resonance Io shares with its neighboring moons Europa and Ganymede. The heat generated by that flexing is enough to drive hundreds of active volcanoes, to keep the surface of Io perpetually resurfaced by eruptions, to make it one of the most geologically alive places known. The TRAPPIST-1 planets occupy a resonant chain with a similar structure, though the gravitational conditions differ significantly, and the degree of tidal heating across the system remains uncertain. For the inner planets, the tidal contribution may be enough to drive volcanic activity. For the outer planets, it may be just enough, combined with radiogenic warmth, to keep a layer of water liquid beneath the ice. Whether that liquid zone exists is a question science holds honestly. No measurement has confirmed it. No observation has ruled it out. The densities point toward large water fractions. The physics of tidal and radiogenic heating suggests a plausible heat source. The temperatures at those orbital distances are low, but not impossibly low, given enough internal warmth. The picture is consistent. Whether it is correct is a question for instruments not yet built, or perhaps for instruments already in orbit, learning to read signals faint enough to require years of accumulation before they speak. What would that hidden ocean look like, if it is there? The question is not answerable in full, but the imagination can move carefully along with the physics allows. The ice above would be thick. How thick depends on the balance of heat coming up from below and cold pressing down from above. Kilometers, almost certainly. Tens of kilometers, possibly. The ice would not be still, warmed from below and cooled from above. It would circulate slowly over geological time, the way Earth's mantle circulates, a creeping, immeasurably slow overturn. At its base, where the ice meets the liquid, the temperature would hover near the freezing point, not because the ocean below is barely warm, but because water at extreme pressure has a lower freezing point than water at the surface, and the geometry of the interface is set by that pressure-adjusted threshold. Below the ice, the ocean, its depth unknown, its chemistry unknown. Whether it is saline or fresh, mineral-rich or sparse, oxidized or reducing, all of this is unresolved. On Earth, the chemistry of the deep ocean is driven partly by contact with hot rock at hydrothermal vents, where seawater percolates into the crust, is heated, dissolves minerals, and rises back into the water column, carrying iron and sulfur and silica. If the floor of a TRAPPIST subsurface ocean is rock, and for the outer planets with thick water layers, it may instead be a form of high-pressure ice. The chemistry of that contact will be different. It will be its own thing, shaped by pressures and temperatures and rock compositions that have no exact parallel in any ocean on Earth or beneath any moon in this solar system, and will need to be understood on its own terms when the instruments exist to reach for it. The ocean floor, if it is rock, would be dark. No starlight reaches it. No bioluminescence exists there yet, in any form known. The water would absorb what little heat rose through the rock, warming very slightly near the floor and cooling upward through the column. It would move, convection cells, driven by temperature differences, slow and vast, turning over on timescales of thousands of years. The silence would be complete in the way only deep water can be complete. Not the absence of vibration, but the presence of a medium that carries vibration strangely, absorbing some frequencies and transmitting others, so that sound in the deep ocean is a different kind of sound than sound in air, lower and more traveling, reaching across distances that would fall silent in any other medium. There is something in this that asks to be held quietly, an ocean that has never been touched by light, warmed from below by the slow decay of atoms and the grinding of tides, sealed above by miles of ice, circulating in the dark on the time scale of civilizations. And this, possibly, on 3 separate worlds in a single planetary system, around a single small star, 40 light-years away. 3 hidden oceans, or 1, or none. The honest answer is that the number is not yet known, and may not be known for a long time, and that this uncertainty does not diminish the possibility. It simply leaves it open, which is where it belongs. The surface gravity of TRAPPIST-1G is estimated at roughly 80% of Earth's. A person standing there, on the ice surface, if there is an ice surface, in whatever thin or thick atmosphere the planet has managed to hold, would feel slightly lighter than at home, not dramatically so, not the floating lightness of the moon, just slightly less pressed to the ground, as if some fraction of weight had been quietly lifted. Beneath their feet, miles of ice. Beneath that, ocean. Beneath that, perhaps more ice, and then rock, and in the rock, the slow warmth of atomic decay. TRAPPIST-1 FEF carries a similar picture. A radius near 1 1/4 times Earth's, a mass near 1 1/3 times Earth's, a density that, like its neighbors 1G and 1H, points toward a substantial volatile fraction. Its surface gravity works out to roughly 87% of Earth's. It receives about 38% of the energy Earth receives from the sun, a faint warmth, a light that would look dim even by Martian standards, reddish and low energy, falling on an icy surface with no real power to melt it from above. Whatever liquid exists on or in this world would need another source of heat, and the interior provides one, quietly and steadily, the way old stones hold the warmth of a summer day long after the sun has set. The resonant chain that keeps all 7 planets in their synchronized orbits is not simply a structural curiosity, it is a physical memory. Resonances of this precision involving this many bodies do not arise spontaneously from random orbital placements. They form when planets migrate, when they drift inward through a protoplanetary disk of gas and dust, losing energy to the disk material and spiraling gradually toward the star. As each planet moves inward, it can be captured into resonance with the one before it, the gravitational tugs locking the period ratio into place, the 2 planets then moving together like linked gears as the inward drift continues. One planet captures the next, and the next captures the one behind it, until the chain is built, 7 worlds linked in mathematical synchrony, their periods reflecting the history of a journey that ended billions of years ago. The rock that now makes up their mantles, and for the outer worlds, their floors beneath the ocean, was gathered in a colder part of the disk than where the planets now reside. It carries the composition of cold outer disk material. That material was rich in volatiles, water ice, carbon dioxide, ammonia, other compounds that evaporate easily under heat but persist in the frozen outer regions of a young planetary system. As the planets migrated inward and the disk warmed around them, some of those volatiles were lost. How much was lost and how much was retained and later distributed through the interior depends on the rate of migration, the temperature history of the disk, and the early activity of the young star, none of which can be recovered in full from current observations. The water that may now fill an ocean on TRAPPIST-1 for 1G was gathered in a cold place and carried inward over millions of years by the slow gravitational architecture of a forming planetary system. It arrived at its current depth through a process so long and so gradual that it leaves no single trace, only the density, that single quiet number, speaking of what must be inside. There is a particular kind of stillness in thinking about this. The ice that may seal the outer TRAPPIST oceans has been in place, if it exists, for billions of years, not thousands, not millions, billions. The ice at the surface of TRAPPIST-1 has sat in the faint reddish light of its star, changing slowly, perhaps being reworked by impacts, perhaps being maintained by a thin trickle of interior warmth, just sufficient to allow a slow turnover in the ice column for longer than the Earth has had complex life, for longer than there have been fish in any ocean, for longer than there have been continents in any modern configuration. The ice is old in a way that makes geological time on Earth feel recent. TRAPPIST-1 itself, the outermost planet, sits at the far edge of the family. Its orbital period is roughly 19 Earth days. It receives only about 14% of the energy Earth draws from the sun. Its equilibrium temperature, the temperature a bare body at that distance would settle to, without any greenhouse effect, is far below the freezing point of water. Whatever warmth it carries is almost entirely internal, radiogenic, tidal, the slow dissipation of the heat of formation. Whether that warmth is enough to sustain anything liquid is among the most genuinely open questions in planetary science, and it will remain open for some time. The mass of TRAPPIST-1H is the least well-constrained of the seven. The signal from its gravitational tugs on its neighbors is smaller, both because it is the outermost link in the chain and because its low mass, estimated at roughly 3/10 of Earth's, means it pulls less strongly on the others. The uncertainty in its mass touches 20% or more in some analyses, which translates directly into uncertainty in its density, and from there into uncertainty about how much water or ice it might carry. The picture is consistent with a large volatile fraction. It is not confirmed by it. What can be said is that this small, cold, faint world at the edge of the TRAPPIST system is not obviously incompatible with having an interior that is partly liquid, and that this, given its extreme distance from its star and the faintness of any external warmth, is itself a quiet and considered finding, not a proclamation, not a certainty, a quiet finding held at the appropriate distance, which is the only honest posture science has in the face of something this remote. The system has been observed now for years by telescopes on the ground and in orbit, by instruments built for other purposes and adapted to this one, by a community of scientists who have spent careers on these seven small worlds and their small star, building the picture one transit at a time. The masses are constrained, the radii are well measured, the densities are calculated. From the densities, the broad interiors are sketched in pencil rather than ink, likely silicate rock here, likely substantial water there, uncertain transitional compositions in between. A gravitational field here, almost indistinguishable from the one in which the entire history of life on Earth unfolded. What the measurements cannot reach, and may not reach for a long time, is the inside of those interiors. Whether the water on the outer planets is liquid or entirely solid, whether tidal heating is sufficient to sustain a liquid layer or not, whether any of the worlds have active geology, eruptions, plate motions, the cycling of rock and volatile material that on Earth has helped regulate the climate and chemistry of the atmosphere over billions of years. These questions wait, not in urgency, but in the patient way that scientific questions wait when the instruments needed to address them are still being designed or launched or calibrated. What can be said with the confidence that density and mass and resonance allow is that these seven worlds are real and various. They are not copies of each other. The innermost are dense and rocky, probably dry on the surface, shaped by heat and proximity. The middle ones, and TRAPPIST-1 Ian in particular, carry densities and masses and gravities that place them closer to the physical character of the Earth than any other planetary system yet identified. The outer ones carry something extra, a lightness built from water, a vast volatile fraction that shapes their interiors into something more like an ocean world than a stone world, sealed and dark and deep, 7 worlds around one small star, and somewhere in the arithmetic of their shadows, in the slight delays and advances of their transit times, in the densities inferred from the behavior of light, in all of this, patiently assembled over years by scientists comparing numbers at telescopes on cold hilltops and in mission control rooms, and at desks long after midnight, somewhere in all of that, the outlines of real places emerge, not imagined ones, not the invented worlds of old speculation. Actual planets, with actual compositions, actual masses pressing down on actual interiors with actual internal heat and actual orbital history stretching back through more time than the human mind can comfortably hold. The ice on the outer worlds, if it is there, is old beyond any familiar measure. It formed early in the system's history, when the star was young and active and the disk had recently dissipated, when the planets were still settling into the orbits they now hold. The heat that keeps any liquid zone alive beneath that ice has been flowing upward, very slowly, ever since, rising through rock and ice, warming the base of the ocean, keeping that liquid layer from freezing all the way through. It has been doing this without interruption while every species that ever lived on Earth has risen and flourished and been replaced, and the star above has barely changed.